All right. Uh, Thank you so much for taking the opportunity to join me today. I really appreciate your time. Welcome to my defense on incentive mechanism design for blockchain networks. So we try to talk about bridging decentralized exchanges, Web 3.0, and then the metaverse. So to start with, we go through the introduction of our work, and then we introduce some the preliminaries of our research, and then we proceed to show in some work examples, and then we conclude our dissertation. But to give you an overview, the entire thesis is based on the main objective of the thesis is decentralized exchange integrity, and then sustainability of Web 3.0 and the metaverses, and then the next thing is blockchain proof of stake network reliability. All right, so to start with, to give you a brief overview of the decentralization of the internet. So that's the evolution of the internet. The internet evolved from Web 1.0, that's a static representation of the internet that we have so many years ago. So you can only get feedback from the internet. You cannot interact with the internet. You only read from the internet. And then we migrated or we evolved to Web 2.0. And then in the Web 2.0, we could interact with the internet. We could also read, share, comment, and then it's more like a social web as we have now. And then the drawbacks to this is data privacy, exploitation, and then government censorship or a lot of government interventions and all that. So the reason being that is like sometimes our data is being sold, but we do not have the control over the data. As we can see, the major giants use those data to generate revenue and all that, which is undesirable. So the next evolution of the internet was to decentralize the internet. So in decentralizing the internet, it relies on some technologies that are very fundamental to our work, which we'll introduce later. All right, so take for instance, what is centralized and decentralized finance? So usually the traditional way when you have what we have now, when one party wants to sends a transaction to another party, what happens is the transaction goes from her bank. Say Alice wants to transact with Bob. Her transaction goes from her bank and then goes into an intermediary check system and then moves to Bob's bank account and before it reflects. So that's the form of a centralized finance that we have. We have a lot of entities that are in between that controls the steps taken to in our transaction. But then when we talk about decentralized exchanges, so no intermediary is required. Everything is done on a technology called blockchain, which we'll introduce later. So blockchain has a very cool feature called smart contracts or protocol like called smart contracts that you can execute autonomously to make sure there's no third party that's involved in the system. Right. So some of the advantages we can get from decentralized finance would be global accessibility, its resistance to censorship attacks, and then direct ownership and control because there is no intermediary in between. I control my data and then I control where my data can be sent and all that here. And then the next thing we want to talk about is a metaverse, which is also fundamental to the technology that we use in this research. So metaverse is just we have a lot of buzzwords later last year and this year, especially with Vision Pro. So metaverse is really just a virtual universe of interconnected digital environments. So they merge physical reality with digital reality. And then why is everyone making a buzz about it? Because it's going to revolutionize the internet. So the next thing is some work related to metaverse that we have done in my PhD studies would be HD map optimization. So what happens is we have vehicles, we do some form of like simulation in the metaverse where vehicles are driving and we want to send some HD map, highly dynamic data information to the server to generate HD map updates for us. So what happens is taking camera frames or video frames and then transmitting it to the server becomes the transmission size it comes into question in this problem. So what we try to do, we try to optimize the transmission before sending to the server. So the server knows the key important things that it needs to use for its map updates. So what we did in this work is we take the areas of importance that's like the vehicle, pedestrians, or any object that's of importance to us. We maintain the quality of those frames in our camera frame, and then what happens is the ones that are not important to us, we just compress them out. So how do we achieve this? We go ahead, we perform object detection first, and then we divide the results into grid, and then we try to compute the percentage area of the grid that's used. That's like which percentage of the grid that our object uses, our detected object uses, and then the areas that are not used, we just compress those pixels out, and then it dramatically reduces the size of the data to be transmitted for HD map updates. And then the next thing is, so after doing the HD map updates, we need to select which vehicles, all the vehicles could send map updates to the server, HD map information to the server so the server can generate updates for them. But it's undesirable because some data will be redundant if we are in the same zone. So what we try to do in this work is and perform the HD map optimization. And in attempt to transmit the data, we try to use a reinforcement learning algorithm, that's a machine learning algorithm, to select which vehicle that's most suitable to transmit data in any given region. And then the third metaverse work, which was recent with Toyota, is we try to integrate AR VR headsets into autonomous vehicles. So we try to leverage eye tracking, head movements, and then voice commands. So we try to prepare this platform so when blockchains or the Web 3.0 is integrated with metaverses, we will be at the forefront of this revolutionary technology in metaverses. All right, that's just a quick example of how we perform the object detection on the HoloLens, that's the AR, VR headset we use. And then we send information to the server to be processed, we return the information back. So using some edge computing paradigm. And then this was a very great experiment. I really enjoyed it. And then the next part is, so all of this is Web 3.0, decentralized exchanges, and the metaverse works that we have. So all of them fundamentally depends on the blockchain network. So the blockchain technology underpins the infrastructure of the Web 3.0, decentralized exchanges, and metaverse, which provides the mechanisms for secure, transparent, and then decentralized operation. So for all this time, I've been mentioning blockchain, blockchain, blockchain. What are blockchains? So blockchains are distributed, decentralized digital ledger that exists across peer-to-peer networks. So we have centralized systems that will be the traditional banking systems we have now, and then distributed will be BitTorrent, and then decentralized will be Bitcoin, or so many other evolutions that we have now. So what does a blockchain look like? So it's a series of blocks appending with each other. And each block has a block header that has some kind of information and then some number of transactions that are in that block. All right, so what are the key properties of blockchain that we really care about that makes us leverage it in all the technologies I've introduced? The key is one, decentralized ledger. It provides a decentralized ledger so everyone on the network has access to that ledger. Two, immutability. It can be changed. Information reading cannot be changed by any single entity on the blockchain network. Three, transparency. Information is available for everyone to see since it's a decentralized ledger. Next, consensus mechanism. We come to agreement on how blocks are going to be added on the in the blockchain system. And then some other improved technologies that we want to talk about is cryptography. So we ensure the data integrity and security on the blockchain network. And then finally, smart contracts, self-executing contracts that perform given tasks. All right, so now in our area of studies, we have a cryptography that involves that involves a lot of ensuring data integrity and then security on the blockchain network. That's one school of thought. But then the problem with this is they always assume that the blockchain network is lively, and then we are going to continue having rational participants on the blockchain network. So they fundamentally lack the relevant incentive mechanisms designed for this distributed infrastructure, because cryptography can ensure that the data is secured and the integrity of the data is ensured using ZKPs and so many other technologies. But then how do you ensure that the rational participant on the blockchain network and we ensure that blockchain people are able to participate over time? So that's where we come in. So we come in a form of crypto economics where we try to introduce economics into our blockchain infrastructure. By so doing, we handle the human interactions or the rational behaviors of participants on the blockchain network, so which involves a lot of incentive mechanism design. How do we design incentive mechanisms, and what are some of the incentive mechanisms, incentives we can offer? That's what we answer in the next slide. So we can offer rewards that will be in form of block reward or transaction fee. We can also offer penalties that will be in terms of like security deposits or slashing users. That's one of the greatest techniques that blockchain has recently introduced. Next is we can offer privileges that will be voting weights. So finally, what are the techniques that we use to design incentive mechanisms? We have auction theory, we have game theory, and we have contract theory. Contract theory will be our fundamental kung fu in this research. But then we try to increase as the depth of our research increases, we try to integrate other techniques as well from game theory to make sure our technique is a little bit robust and then enhanced. All right, so right now, to know the fundamentals of contract theory, we talk about if information asymmetry levels. So what are information asymmetry levels? One, adverse selection problem where someone knows an information that you do not know, so that person has a leverage. That becomes an adverse selection problem. So here, when I started with my PhD, I told my professor I wanted to be a professor when I graduated, and then I would want to continue down his path, have a lot of publications, mentor a lot of students, and all that. Unfortunately, he has actually now found out that I do not want to be a professor. That's an hidden information that I have in the first time of contracting. That makes it an information asymmetry level between my professor and me. Assuming he knows that he'll probably not employ me as his student. But now he knows. So that is one of the information asymmetry levels that exists on the blockchain network. The next one is moral hazard. Moral hazard is how much effort do I put in as a PhD student? So my professor doesn't know the amount of effort I put in throughout my PhD studies. And that way, if he actually knows, then he can make some measures or know how much effort, how much input to output to expect from me. All right, and then so in a nutshell, my parents think that I'm a great professor at what I do. I in robes and then make great exploit. But then what my professor actually thinks I do when he's present and when he's what he actually do things I do when he's absent. That's just illustrating the moral hazard problem and then the adverse selection problem. All right. Now, the key problem with incentive mechanism design, we have already introduced information asymmetry level. So what are the key challenges in designing, in handling information? If you know there's information asymmetry level that exists between people, you can just, hey, tell me your information, I tell you mine, then we carry on with our business. But it doesn't happen like that. It's because most people are anonymous. We don't know them when we are interacting with them on the blockchain. And next, they are rational. They want to maximize their utility and they are not willing to tell you their private information. And then the next thing is, yeah, the private information is hidden to them. They do not want to volunteer that. And then the last thing is there is a large participant of people on the blockchain network, which makes it harder to handle information asymmetry levels. So in using contract theory, we are able to design adverse selection problem, moral hazard problems, and then we integrate some form of we use that for incentive mechanism design, given that we need some information so we can incentivize people to behave well on the blockchain network. And some of the rewards that we also introduced earlier will be incentives we also introduced earlier will be rewards, penalties, and then privileges. Yep. And then that brings us to our first work. Our first work in this research will be incentive mechanism design for mitigating front running and transaction reordering in decentralized exchanges. All right. So what is transaction front running? Transaction front running is putting your transaction, assuming I put a transaction on a block, say Alice puts a transaction on a block. And then I see, okay, this transaction has a valuable, it has have some value, and I want to front run it. What I can do is, what anyone would typically do is put in transactions and increase the gas fee so they get their transactions executed earlier or before Alice's transaction. And then we have more participants putting in transactions on the blockchain network to front run Alice's transaction, which is they typically call the transaction front running. And then usually when a miner has a fixed number of fixed number of transactions that can fit in a block to create a block. So assuming in our case we have a limitation to take four transactions. In this case, the miner would only include the transactions that pay the highest gas fees. That would be 70, 50, 40, and then 20. So at least transaction never gets executed. By so doing, the miner can have a higher form of reward or gas fee. So now what happens when a new transaction comes in and then they increase their gas fee to maybe 90. So the miner could go ahead and reorder the transactions to kick out the gas fee with 20, then he gets even more rewards. So that we call transaction reordering, and then which brings us to something called maximal extractable value. So maximal extractable values are basically adversarial ways to order transactions or front-run transactions in the blockchain network to get to extract some value from users. So related works in this area includes the first sequencing services, that would be first come, first serve. The second one will be auction theory, where we auction off the right to order transactions on the blockchain network. And the final one will be automated market maker. So we try to predict the gas fees before the transaction in time, so we can know how much we might pay or how much we might not have to pay for any transaction at any time. The key fundamental drawback to all these approaches, there's an existing, so we come from the crypto economics background. So we try to find out what kind of information does all the parties need to be able to ensure proper behavior on the blockchain network. Proper behavior means you do not do the front run, or you do not try to reorder transactions on the blockchain network. So we talk about the private informations that the users have about their transaction, that if the miner knows, the miner will make informed decisions on how to order transactions on the blockchain network. What are those private informations? They include transaction revenue. That's the transaction revenue would be not in terms of how much money the transaction makes, but the evaluation of the transaction revenue. So assuming we have Binance and then we have Dr. Han transacting on the blockchain network, Dr. Han's usual transaction will be smaller in terms of value compared to Binance, a big company. So that way, if the miner knows that, hey, you are a big company, I can charge you a little bit more. And then if you are just a single entity, I can charge you a little bit less, or it's reasonable to pay this amount. And then the next thing, so the key things we want to address that motivates this work is we want to prevent MEV centralization and then incentivize honest behavior on the blockchain network using complex private data, and then implement multidimensional contract designs that extracts this private information for us. So our contribution will be, as we see in a few slides, will be weighted transaction ordering mechanism, which I'll introduce in a bit, and then how weighted transaction ordering mechanism is achieved through multidimensional contract designs. All right, so in a nutshell, to just give you a brief overview, we have possible users revenue, that's a private information they would not want to give. Their delay tolerance, how long do they want to wait to get their transactions executed? Also another private information that a miner needs so that he can make informed decisions on ordering transactions on the blockchain network. So knowing these two, we can better serve users on the blockchain network. So how? We talk about our system model that includes step one, users submit transactions on the blockchain network. Step two will be we offer contracting, and then we offer a variety of contracts to the users. And then the users then select a contract that reveal their type. So when you select a contract that's for a high type, a high value type, then we kind of know, oh, okay, you have a lot of stake in this business, so maybe this is your type, and this is what the miner needs to do in the next step. And then in the third step will be, now we do the transaction ordering, and then we order the transactions based on the scores from your type, your extracted type, and then we send the transaction back into the mempool for miners to pick from and execute. So we make sure that will give them their optimal rewards, so that if they try to deviate from it, there are some consequences later, as we'll see. Our utility function includes an indicator function that talks about ensures the timely submission of blocks on the timely execution of transactions. And then we have the reward paid by users to the miner for mining a block or adding their block into their block. And then we have the workload of the transaction revenue. That's a probability of being a particular type distribution of the transaction revenue. And then we have the transaction workload. And then for the user's payoff will be their evaluation of that transaction. What do I think this transaction is worth? And then their evaluation will take in form of how much revenue they make from that transaction, and then their delay tolerance. Then you try to how much, and then you try to subtract that from how much they actually pay the miners for mining their block. That's basically how we design our system, our simple system model. Now, the next thing is the contract design for users includes a complete information scenario and incomplete information scenario. What are these? A complete information scenario is when we know the user type. It's easy because, yeah, you tell me you are a rich guy. Okay, maybe I tax you a little bit more. I take some little bit more from you. If you tell me you are a poor guy, maybe I take a little bit less from you. So we know the user's type. So the key thing about this is if we know the user's type, then our constraints become individual rationality. What is individual rationality? Is to make sure that if people are contracting on a blockchain in our system, they do not get a negative payoff. Their payoff is always going to be positive. That way we can ensure people participate in our system. And then the next part is if we do not know the user's type, then we do an incentive compatibility constraint. That would be okay, so if you pretend you are a type that you are not, then your payoff should obviously be low. When your payoff is low, it disincentivizes you from pretending on the blockchain network. And then this is an overview of the two contracts we offer to the users to extract their type. And then, so our whole system design comes in form of contract one, complete information scenario, contract two, incomplete information scenario. Then we get a user's type from those two contracts based on their selected contract by the users. And then we use that to formulate some weights that are appended to the transactions. These weights determine which transaction gets executed before the other. That is how our overall system design works. And then based on that weight, we can categorize some transactions as very high priority, medium priority, and a low priority. All right, so over in our work, that's the overview of everything we did in the first work, and then the results we obtain will be the average minus utility is improved. Because we get we get the user's type, the miner can make informed decisions on ordering transactions on the blockchain network or executing transactions, which enhances the miner's utility. And then by leveraging the multi-dimensional contract designs. And then the next thing is the average user's payoff analysis. So the user's payoff is also enhanced because when we leverage the multi-dimensional contract designs, users do not pay too much money in executing their transactions because then we're able to know their type and know how much they should pay for their transactions. Now, the summary of the first work would be we use contract theory as our major kung fu again, and then we develop we develop multi-dimensional contracts. We extract the user's information, and then we compute the weights, and then the weights are used to sort transactions on our blockchain network. The key things we use will be adverse selection problem, and then we have something called decentralized oracle networks. The decentralized oracle network essentially is just the nodes on the blockchain network that we assume should not are truthful. So it combines like a mini consensus mechanism on how how our algorithm is going to be run and how our transactions are going to be ordered on the blockchain network using our algorithm. And then the incentives we offer users will be rewards. Now, the next work will be promoting the sustainability of blockchain in Web 3.0, the metaverse, through diversified incentive mechanism design. As you can also tell, again, we have another form of incentive mechanism design that involves some form of tools that we use from contract theory and then some kind of rewards. Let's go through together. All right, so full nodes are the fundamentals of blockchain network. They hold all the data of the blockchain network. But then the problem with full nodes is they are very expensive to develop, maintain, and then they are very expensive, especially you have to pay for internet, you have to pay for storage, storing the entire block, the blocks from Genesis block, and so many other maintenances that are associated with full nodes. Other nodes could be archival nodes that stores partial information, but then also massive. And then if you want to start your blockchain in your room somewhere small, you could use light node. The problem with this is because of the cost and the maintenance and everything involving full nodes. Well, a lot of people would not be incentivized to develop full nodes. They can just start with light node because they don't stand to benefit anything from the blockchain network. Now, what happens if there are decreased number of full nodes on the blockchain network? We have problems like scalability issues. We have poor quality of service because then the system is micro centralized. And then that's the centralization we also talked about. And then finally, suboptimal optimization because some group of people on the blockchain who develop full nodes can decide how on the governance of the blockchain network. Now, the research questions would be, okay, so again, we use crypto economics. We look at it from the economic aspect. What information do we need from users and then a blockchain network so we can make sure we incentivize people to develop full nodes on the blockchain network? And then giving that information, if there is reward, how can we make sure the blockchain doesn't, with the payment of these rewards doesn't breaks the blockchain networks or the employer's bank? So key contributions would be another one, incentive mechanism designed to address adverse selection problem and the moral hazard problem we'll see in a bit. And then we diversify the incentive so that the blockchain network doesn't pay too much in terms of monetary rewards. So what we try to do is, what are the information asymmetry levels that exist? The blockchain does not know the node implementation of the user, and he does not know the capability of the user in terms of how much computational power they have, their configurations and all that. And then the next thing is it does not know how much effort the users put in maintaining the blockchain network. So these are the adverse selection and then the moral hazard cases in our blockchain in our system. So to resolve this, again, we formulate our utility function, but then our utility function or utility model will have the key benefactor of our full nodes are the Ethereum blockchain network. We take an example. It could be any other blockchain network, but the key person have benefits is the Ethereum network. So the blockchain. So what happens is that blockchain is obliged for the blockchain to incentivize people so that it can continue to sustain itself. And then why doesn't it so that people can develop full nodes that sustain it? And then the other entity involved in our system will be Ethereum users. So in our utility model design, we have the payment to the platform for using the blockchain nodes. And we also have things like probability of generating high revenue and then reward paid to users. So that comprises the Ethereum network's utility function. And then the Ethereum users utility function will be the revenue they generate, because there are sometimes where you develop full nodes to use for your business. So you end up generating revenue from that. So that revenue you generate plus the reward the blockchain pays you for developing full nodes. And then we talk about the cost you put in developing the full nodes. So to sum up, our first problem formulation for the second work would be we want to maximize the utility function of the Ethereum network, and then subjected to, again, incentive compatibility, individual rationality, and then the next thing we introduce is monotonicity constraints. That talks about if you put in more effort, then your reward should be higher. And then so to formulate this problem, we talk about all the various information asymmetry data levels, and then see how the significance, or see how it affects our system so we can know the best design to use. In our first work, we only use adverse selection model. Here we experiment with moral hazard, we experiment with adverse selection, we experiment with the two of them to see which one will give us the best the best results. So then in our problem formulation, we break the major problem formulation down into just moral hazard scenario, adverse selection scenario, and then both of them, like I just mentioned. So what happens here is to offer you some insights in the moral hazard alone. So what we do here, we try to remove anything that insinuate some kind of adverse selection related to adverse selection. That would be probability distribution of users. It's giving you some kind of information about the user's type, which is an adverse selection problem. So we remove that from our system design, and then we try to solve our problem. And then in adverse selection only is we fix the effort level for every user. So then we know that the effort does not affect the system in any way, and then we solve our system. And then in both scenario, we try to integrate the adverse selection case and then the moral hazard case together to solve our problem. The key insight we obtain is when we only use a moral hazard scenario, the rewards are based on the outcome of the effort. And then there's a risk of overpaying due to unknown potential. So when I use the blockchain network to develop full nodes for my business, and then the network is going to think that, hey, he has full nodes, he maintains it, he has this amount of resources that is contributing towards the development of my sustainability, I need to reward him more. And then they don't know that I actually also use the full nodes for my business. So that we usually moral hazard scenario, we get a problem of a challenge of overpaying users on a blockchain network. And then the converse of that is adverse selection scenario. We observe that the rewards or incentives are paid based on inherent capabilities. So if you have a high computational, high maintenance, and high contributions towards full nodes, you get more. But then we can also we also outlook the effort that the users put in, which is or which provide the next challenge in just adverse selection only. Now, the combination of the two of them offers a better system where it prevents us from overpaying or underpaying users on the blockchain network in our system. So then we proceed to go with both scenarios case. In the next slide, we see the results from the both scenario case. So just before we move to the results in the both scenario cases, the next step we want to do is we have obtained the insight that our both scenario, that's adverse selection and moral hazard, is the best for us to use. Then what then we have to do is we want to diversify the incentives. Why do we want to diversify the incentive? Because we do not want to end up paying too much monetary rewards to users on the blockchain network. We want to incentivize users so that they can get some other forms of incentives when they participate in full nodes. And then those other forms of incentives should be equally important and useful to users. So here we talk about voting rewards. So when you're a high type user and then you have accrued rewards at a certain level, we can convert that reward into voting points for you. That's basically what we did in this work. How do we do the conversion? We use techniques from macroeconomics or microeconomics called indifference curve. So it's a range of it's usually in economics it represents a collection of consumption bundles towards which the user is indifferent. So if I give you 5 Cokes for 2 burgers, are you okay with that? And then if I give you no, you tell me no. Then okay, well, what about 10 Cokes for 2 burgers? You say yes. Yeah, that's a kind of rip off, but that's more like the indifference curve. So we use that to simulate our voting points and then our monetary rewards. So how much voting points is equivalent to our monetary rewards? Then we're able to get a particular fixed point where users are indifferent. That point, it will be the marginal rate of substitution where or what that's found on the indifference curve where users can trade off one value for another. And then next thing is like I said, the reward, the results. The results, the Ethereum network utility is highly improved. And then based on using both moral hazard and then adverse selection, only combining the two of them, we're able to improve the Ethereum network's utility. And then also one thing that also dramatically improves the network's utility is diversifying their rewards, because then they do not have to pay a lot of incentives in terms of money-wise to blockchain users. And then the next thing will be a quality of satisfaction for the users participating on our system. So in this, we talk about the key insight we can obtain from this is the red line is 0.5, where anything above 0.5 shows that our system, people are satisfied with our system. Anything below that shows people are not satisfied with our system. So we can see from the graph that our users are highly satisfied with the system. And then why are they highly satisfied with the system? Because we offer them some form of incentives for developing full nodes in the first place. And then we diversify the incentives so they can have a range of values to choose from, or a range of incentives to choose from. All right, and then summary of the second work, again, we use contract theory. We introduce a little bit of complexity where we use adverse selection and moral hazard case. And then the next thing is in terms of incentives, we offer rewards and privileges. And then for our final work in this dissertation, we talk about a contract Stackelberg framework for mitigating timing games in proof of stake blockchain network. So it looks a little bit technical, but let's go through it together. So what happens here is, just to give you a background, what happens on a proof of stake blockchain network is Alice, Dan, and Bob stakes put up a stake, usually 32 ET, and then they try to put that stake to be selected in hopes to be selected to be a validator. So we have a validating function that selects that picks a validator from that randomly picks a validator from Dan, Alice, and Bob. So what happens? Okay, Bob gets selected to be the validator of the next block. So what Bob does is Bob adds new block and then receives block reward from adding the new block. And then if the block is checked and then valid using cryptography means, then Bob's gets to keep his reward, and then we go through the cycle again, selecting a new validator. But if it's invalid, then Bob's stake is burned or slashed, and then we go through the cycle of selecting a new validator to add a block. Now, what happens if, assuming Bob is very greedy and then smart, and then he wants to maximize, want to obtain a maximal reward on the system? What he can do is he gets selected to be a validator. It's time to submit a block. And then what happens next is the original time to submit the block is 1 p.m. So Bob can go ahead and then manipulate his system clock, and then that's push him a little bit forward in time. Then he can accrue more block rewards. This is undesirable on the blockchain network because then he gets to accrue more block reward, but it essentially breaks down the fundamental key concept of the blockchain network. And then what happens next is there's something called cyber attack that's going to be, so he knows that his time to be a validator is almost over. So what he does is create multiple nodes, give all those nodes a minimum stake to be selected as a validator. We have the validator function runs through a lot of validators again. And then assuming one of Bob's so many other nodes get selected by our validating function. So then Bob gets to order the transaction again. And what he does is he goes ahead, and then he manipulates the system clock again, and then he tries to accrue more block reward. There are so many ways we could fix this problem. We could talk about using some form of like clock synchronization. And then so what happens if someone pretends to move to another state over like moves dramatically and all that. So that's a lot of like the technicalities of solving this problem. You could also use slashing and so many other mechanisms. But for us, we are looking at the economic incentives that drive this behavior. So essentially, why is Bob behaving this way? Assuming we want to have an ideal system, what would that look like? Obviously, Bob is not going to behave this way. So how do we design this system? That's what we want to look at in this work. So now the motivations I just talked about earlier, I just introduced it in a bit. And then the challenges would be, okay, conflicting interest between the validator and then the blockchain network. What is this conflicting interest? The validator wants more money, wants to accrue more rewards, and the blockchain network needs transaction to be submitted on time and not extracting MEV from users. And then now the other thing is the dynamic nature of the blockchain. So we can't design one size fit all, where we say, okay, just everyone synchronize your clock, and then that's fix the problem. We are essentially for ignoring the motivation behind this attack. So I try to attack the motivation. So when we're able to resolve the motivation, our problem is solved. So here we propose a contrast Stackelberg game, which we'll look at in a bit. And then the contributions will be, we categorize validators on their types. And then based on your type and your behavior, we're able to get that kind of user types from asymmetric contract designs. And then we do a Stackelberg game alignment to align the interaction or the various strategy between the users and then the blockchain network. So to take a look at, we have introduced the timing games earlier. And then what happens is in our new model, in our system design, we offer contracting. So contracting will be, we offer you contracts, to be like, okay, fine, assuming we know this kind of information about you. So that would be, hey, your revenue type and then your effort level. So the revenue will be how much block reward you might end up making from submitting block on time, and what's your opportunity cost if you do not submit on time. And then the next thing is the effort level, how much effort you put in submitting block on time. So when we get that information, then we develop our contracting model. So what our contracting model does is it gives us the user's type. It extracts the user's type for us. When it extracts the user's type, we can know how the blockchain network can design its incentive. So after designing the incentive, it becomes like a game because it's going to be an iterative thing that happens over time. So we try to use a stackable game model. And the game model, the first stage will be the leaders a reward allocation. So I'm going to, hey, assuming your effort level is this, and then your revenue type is this, I'm going to give you this reward. See how you react. Do you submit on time, or do you participate in timing games? That would be the stage 2. So that would be the validator's effort level and stake allocation. So to formulate our problem, we talk about what we just introduced earlier. Our utility model for the blockchain network will comprise of the probability, the user type distribution, and then we have something called the block submitted successfully. The block was added successfully. That's all that the blockchain network cares about. It's added successfully on time. And then the next thing is the incentives it pays to the users for participating in the system. And now for our users, we have again, we have a time indicator function here, and then we take how much revenue they make from block rewards plus the amount of incentives that is being paid to them. And then the next thing is we try to take we subtract that from how much efforts they put in submitting block on time, and then something called the opportunity cost. That's how much they miss from not submitting block on time. So to design our system. So in our system design, we take the contract thing, for instance, and then we solve our contract model, we formulate a Lagrangian, and then we solve, and then we try to find the optimal closed form solution to that. And then what happens, we find the optimal stake, and then the optimal stake for the users, and then the optimal effort level for the users. So knowing that, then how can a blockchain network, we take all these solutions, we put it back into our objective function optimization problem to resolve to get optimal incentives for the users that's going to be provided by the blockchain network. And then the optimal time which the blockchain network should set for any kind of transaction. So knowing all of this, the leader's problem, that's the first stage, will be the rewarding position. So like I said, give you this incentive, see your behavior. And then the second stage will be followers problem. That will be their stake and effort level. They choose a particular stake and then the effort level. So what happens is we do a backward induction. So the backward induction, we solve what would be the optimal stake and then effort level in this first iteration between the blockchain and then the user. And then we take that and we put it into the blockchain's optimization problem. We resolve to get the optimal reward that the blockchain should offer the users. And then this iterative game continues until we establish our equilibrium. The key insight here will be the strategic equilibrium that's achieved, that's the Stackelberg equilibrium. It converges to, we are able to convert to SE, that's the Stackelberg equilibrium, where the leaders optimize their utility and the followers adjust their strategy to also obtain their best rewards. And then the next thing is it ensures stability in our system and robustness in our contract designs. So the contract design is enough, but then there's a game between the users. So using the Stackelberg game to further enhance the contract theory provides a robust system that handles a lot of the interaction that occurs between the users on the blockchain network. And then the leader and follower dynamics that we just talked about. So they all respond to each other strategically, which iterates over time since the system is dynamic. And then we're able to handle all this strategic interaction over time. And then emerging patterns will be validated exhibit cooperative competitive strategy. That's what we observed in our work. So they try to cooperate and then compete with each other. So, okay, fine, I want to be the one that gets the most reward. So I'm going to be well behaved on the blockchain network. So they try to test each other and see at what limit can they not get any kind of slash or penalties. The key takeaway from this work would be the stackable equilibrium analysis guides the stable strategic contract design that we introduced earlier. And then we observe that it's critical for sustainable growth in the blockchain network. Why? The results show. So in terms of the result, we observe the blockchain utility. We also observe the validator's utility function. And then the next thing is the equilibrium analysis. There are only two systems that uses. So we use our benchmarks that we use will be uh, uh, using just contract theory, using just Stackelberg games, and then using contract theory and Stackelberg game, and then do not use any of them at all. So we observe that in equilibrium analysis, system also better handles the convergence in our system design. And then the next thing is participation rate is also enhanced in our using our proposed mechanism. So to sum up the third work, so again, we use contract theory, but then we add a little spice of game theory, that's Stackelberg games, and then the economic incentives we offer will be rewards, penalties, and then we get individual rationality, incentive compatibility. We enforce users to submit transactions on time. Next, it's the key problem, the key challenge in some of in our work that we want to address in our future work will be collision in contract theory designs. So we designed our first work failed. We want to make sure users order transactions very well on the blockchain network. Next, incentivize full node implementation. And then the last one will be incentivize timely block submission. But what if validators agree to share rewards, so they collude among each other, so they can behave some type of way? That's like a multi-level hierarchy. So we look at individual wise and then group kind of organization. So group wise, then that becomes a lot of collusion on our blockchain network. So they collude and agree on some rewards, and then they behave a certain way on the blockchain network, so they can all maximize their group rewards. So in that way, our contract theory designs for our previous work have a particular loophole that we want to research in the future. So that would be validators consistently vote on each other's block, and then they try to ignore other blocks, or they vote on each other's wrong time submission of the blocks. So that kind of collision that exists in the system. So in the future, we want to address collision designs. How do we address the collision design? By developing more robust contracts. We want to do zero knowledge proof to ensure that, hey, we have a system that provides cryptographic proofs on how things are done on our system, to avoid a lot of these collisions in our previously introduced mechanisms. And then we also want to use some kind of advanced models like machine learning algorithms such as reinforcement learning, so we can learn zero shot attacks on the blockchain network. So yeah, so we just group a lot of these attacks, and then when people participate in it in the future, we can know this is a group collusion. No, this is unacceptable. So this kind of node is probably malicious. And then we can use, knowing that, we can also do reputation driven system. So based on detecting the attack or the group attack or collusion, then we do some kind of reputation driven system. So that includes our future work. And then to sum up our whole work for this thesis, in the first work, we try to talk about incentive mechanism design that's going to be based on ordering transactions based on users' information. And the next one is another incentive mechanism design that incentivizes node implementation to sustain Web 3.0 and then the metaverse. And then we also introduce diversified incentive mechanisms also in that work. And then finally, the third work would be incentivize timely submission of blocks on the blockchain network. And then these are my publications, and then my patents during my PhD studies, and then finally conclude my PhD dissertation defense. And then I welcome any questions from the audience and then my panelists. Thank you so much for staying with me.